Hello viewers and my dear students. Welcome to problem 8 on analysis of beams. Here I'll be giving you a demo on asymmetrical I section beam analysis subjected to UDL on the upper flange using Ansys Mechanical APDL to obtain bending moment and shear force diagrams. Okay, now the problem is this way. The problem is this, as you see here, this is a beam of length 5 meter or 5000 millimeter. Okay, 5000 millimeter or 5 meters. Okay, it is subjected to UDL on the upper flange. See here, if you take any section here, you can, the view of this from the side, when you look from the side, the section of this is an I section. Previously, we have done a problem where the section of this used to be T section. Now it is I section. This is called flange, this is also flange, but this is web. Okay, but this is on this, this is why it is asymmetrical means the upper flange length and lower flange length are different. Okay, I'll show you how exactly it is different and all that in the section, but upper flange length is smaller, lower flange length is longer, and this is the web. Okay, and this is the cross section of this looks like this. It is an asymmetrical I section. If this and this are same, then we call it a symmetrical I section. Now it is asymmetrical I section, and you have a, you please understand, here we have an UDL 12 kilonewton per meter, or it can also be 12 Newton per millimeter also. Both are same because it's 12 into 1000 divided by 1000. In that way, it can be 12 Newton per millimeter also. Okay. Now see here, an I section with top flange 90 by 10. That is, this is 90 by 10 is the top flange. And web is 150 by 10. This is 150 by 10. Okay. And the bottom flange is 180 by 10. Is used as a simply supported beam for a span length of 5 meters. That is for 5 meters. And carries a load of UDL of 12 kilonewton per meter or 12 Newton per millimeter. Take E equal to 210 GPa, Poisson's ratio 0.27. Determine reaction at the supports, bending moment and shear force diagram using theoretical methods, and use Ansys Mechanical APDL to verify the above answers and all that. It's all same which we can do. Okay, now you see here, this is the flange. This is 90 by 10. This is 150 by 10 web. This is web, 150 by 10 web. Top flange is 90 by 10. Bottom flange is 180 by 10. This is the I section. Okay. Now you see here, this, if you call this as a reaction RA and RB, RA plus RB is 12 into 5 is 60 kilonewton or 60,000 newtons, correct? No? RA plus RB 60,000 newtons. Then you take RB into 5, taking moments about A, RB into 5 minus 60,000 into 2.5. Okay, that is RA plus RB is equal to 60,000. That is, this plus this equal to 60,000, and this 60,000, this total load of 60,000 is assumed to act at the center. That is why 60,000 into 2.5. That's what I have done, and you get RA and RB as 30,000 newtons. That is, reactions that supports will be RA and RB 30,000 newtons. And in the same way, if you do the bending moment diagram calculations also, it is simple. First, a shear force diagram I'll do. This is RA 30,000. This is 30,000. Then at this upward force positive 30,000, since the load is a UDL, it varies linearly. At RA it is minus 30,000. This is how you should get the shear force diagram. This I have done theoretically, which has to be verified in Ansys. Then in the bending moment diagram calculations also, you see here bending moment at B is 0, at A is 0, at this center you see here it is 30,000 into 2,500. This is 5,000, no? 5,000 mm, 2,500. Into 12 into 2000, it is, the remaining is 12 into 2500 into 2500 by 2. Okay, that you should know, it is 12 into 2500, that is assumed to act at the center here, that into this. Okay, that is 12 into 2500 into 2500 by 2. In that way, if you do 0.375 into 10 to the power of 8 Newton millimeter is the maximum bending moment you should get. This is a parabolic anyway, this you have to draw, this you should get. Now, this we will prove it using Ansys. Okay. Now you see here, I have made a separate file. Gurdat Asymmetrical I Section. In the file, change job name, you change it as that, okay. Yeah, Gurdat Asymmetrical I Section and all that I've already done. And even change title also I've done. Change title, Asymmetrical I Section, beam analysis, bending moment and shear force diagrams and all that I've already done. Now we'll directly go for the problem. It's a fresh log file I'm creating under the name Gurdat Asymmetrical I Section. Okay, preferences, structural, say okay. Then preprocessor, element type, add, edit, delete, add you take, compulsory beam 2 node 188 you take. Okay, just say okay and then close. Then under material properties, material models, structural, linear, elastic, isotropic you take, it is 2.1 E5 you take. Okay, and 0.27, this is what they are given, 210 GPa or 2.1 E5 Newton per millimeter square. Okay, in that way 2.1 E5 and Poisson's ratio 0.27 you take. Okay, material you exit. Then under sections, no, under sections, beam common section, here you be careful, here you choose I section now. I section, you see at bottom is W1. W1 from the problem, it is bottom flange length is 180. 180, you see here, top flange length is 90, be careful here, 90. You just look to the diagram what I've already shown you. W3 is from here to here, that web length is actually 150, 150 plus 10 plus 10, it will be 170. 170, be careful. W1 is 180, bottom flange length is more, 180. W2 is 90. This W3 including this thickness, okay, that is 150 plus 10 plus 10, 170. All thicknesses are 10. 10. 10. And 10 you take, okay. Just say okay. Okay. Then once you do this, then modeling you go, create key points in active coordinate system. One you take, 0, 0, 0 you take, apply, 2 you take, I'm taking everything in millimeter, 5000, 0, 0. Okay, then create lines, straight line, you connect this and this, just say okay. Okay, then you go for meshing, mesh attributes, picket lines, take this, just say okay, and take the default attributes. Don't worry about pick orientation, key point and all that. Take the default values. Okay, there is only one material and beam 188 you have chosen, you just say okay. Then size controls, manual size, picket lines, you take this, okay, okay. Number of element division you give 50 or 100 or whatever it is. More the element, more accurate the results will be. I just given 50. Okay, you make 50 and just say okay. Now, you have got 50 divisions here. Then mesh, lines, pick all you do. Once you get, if you go for here list, if you go elements, 50 elements would have been created. As you see, 50 elements would have been created. Okay, now 50 elements have been created. Now, that is pre-processing is over. Now, solution phase you go. Okay. Now, loads, define loads, apply, structural, displacement, on key points. This and this you take, it is simply supported. Okay. That's why, except rotation Z, you rest all degrees of freedom. That you make it 0. Okay. This, that you make it 0. Then, pressure on beams you take. Pressure on beams, be careful here. Pressure on beams, you take box, okay, so that you can select the entire 50 elements at a stretch. Pressure on beams, box you take, say okay. Pressure on beams, say box, you take all the elements here. To make the box, everything you take, and compulsorily you make it to 2. This has to be 2 And pressure at, I've told you 12 kilonewton per meter or 12 Newton per millimeter. 12 and 12 you put it here. Pressure at value I and J, 12 and 12. Just say okay. Okay. Load key value has to be 2. You be careful. You have to make load key 2. Okay. Just say okay. Then this loading is over. Okay. Then once the loading is over, now you will solve this. Solution, solve, current load step you do. Okay, you just have to wait for solution is done message. Solution is done message you got. You are in the right track. Now, till now what you have done is correct. Okay, now general post process. Okay, list results, reaction solution you see. Reaction solution you should know it is 30,000, 30,000. You see a 30,000, 30,000. Node 1, node 2, that is first and last. You have 30,000 and 30,000. That means you are done correctly. This we already proved by theoretical method, 30,000, 30,000. Okay, that is okay. Now you go for, that is element table, define table, add, by sequence number, you see here, 3, apply, by sequence number, 16, 3, 6, apply, by sequence number 3, 6, 16, apply, and then 19. And then say okay. Okay, 3, 6, 16 and 19. I have done this. Okay, then I'll just say close. Okay, now what I'll do is I'll verify the bending moment and shear force diagrams now. I'll go for plot results. Plot results, you see here, under line element results, you know very well, 3 and 16. 3 and 16 will give us bending moment diagram. You see here, perfectly we have got the point, that is maximum is here, that is red there. It is, you see, 0.375 into 10 to the power of 8 Newton millimeter. This is the perfect value what we have got theoretically that has been verified. That is bending moment diagram is perfectly verified. It is this. This has to be recorded. Okay, for the examination and all that is a standard problem which is given in all the universities and all that. And you show theoretically and match using Ansys also. That is 0.375 into 10 to the power of 8. This I told you, plot controls, you remember, write meta file, invert white and black. In that way, okay, you can do this. Okay, invert white and black. This you get that. You get it in paint and all that. Okay, you can save it in the desktop and all that. You can, that is black will become white. Okay, and you can take the printout. This is one thing. Line element results. Then 6 and 19. 6 and 19 will give us the, will get a shear force diagram by this. You see here, shear force diagram 29,400 and minus 29,400. Actually, when we are done theoretically, it has 30,000 and 30,000 here. Minus 30,000. This was plus 30,000. Okay. This, see here. Now I have divided this into 50 elements. More, if you had divided this into 100 equal parts, this would have approached almost 30,000. That's why I said, more the number of parts, more accurate the result will be. That is why I've taken only 50 divisions. When you practice, you divide it into 100 equal parts and see the error will be reduced. Now actually you should have got 30,000 here newtons and minus 30,000 newtons here. Actually theoretically that is the thing. Using Ansys, this is the thing. Okay. Now this also plot controls, write meta file, invert white and black. In that way, this also you take the printout. Okay. Now I have told you here I got the list results, reaction solution we have got, bending moment diagram you have got, shear force diagram you have got. Okay. Now we have come to the end of this session where we concentrated on bending moment and shear force diagram for asymmetrical I section beam. Thank you very much for watching. Thank you friends. Thank you.